I don't think that's worth the effort. Well, anyway, it's 4 p.m., my favorite time of the day. Today, we're gonna finish up animation and then start going into inverse kinematics, which is still related to animation. Mute yourself, Reese.
Oh, sorry.
Inverse kinematics is still related to animation, but it has a slightly different goal than just baking animations, as we have been doing more or less. So, I posted the rest of the assignment schedule on Sakai. I think on this Friday we can start. I can have my extra AR session. We'll do some markerless tracking. We'll check out some of these cool applications of markerless tracking. Some of them won't make as much sense until we get to Reconstruction, which will be later, if not exclusive to the AR section, because we don't see as much Reconstruction in VR exclusively. Then we'll finally move on to forward and inverse kinematics. So just to recap the different mocap methods that we saw, there are active markers, which are these lights essentially. They're usually lights of some type, either these really obnoxious normal lights, or they can just be IR. So normally active markers are used for really complicated tracking scenarios or where there's a lot of interference. So with IR lights you can do this, where you have an IR filter and you can just like cut out all the other light sources except the ones coming from these active markers, which is a nice feature. The problem is that they require a lot of wires and they'll need some power source. Either you can have a power source that's attached to the person themselves, like a battery backpack. A lot of times they have some backpack or satchel that has a battery in it. Other times you'll have this wire like this, which is a problem because then you can only rotate so much before it wraps around your legs and causes problems with Reconstruction. But active markers are still used a lot, and they're an important method in the industry, especially in things like movies, where you have these really complex capture scenarios and a lot of sources of light, especially if you're doing some kind of reconstruction outside, or maybe not reconstruction, but tracking. Here's an example of like one of those backpacks, so that they don't have to. I mean, in an outdoor scene like this, they can't really attach batteries to anything else but the person, so they don't have a choice but to use these backpacks. Then there are passive markers, which are these retroreflective surfaces usually, and what happens is that when you shoot rays of light at them, they will reflect the light back, which is exactly what retroreflective means. Luminosity can be, there are already APIs like OpenCV, which can already track things like luminosity. And there's a system called OptiTrack, which is really common. It's the system where you attach mocap balls to an object that you want to track, and then you have these cameras all around the setup, which there's a camera in the middle of this sensor object, which is searching for the reflective light, and then it's surrounded by these usually infrared LEDs, which are actually shooting the light that gets reflected. So OptiTrack is very accurate because of this. And there's still a lot of equipment that comes with passive markers, but as you can imagine, you don't really need as many markers on the person themselves. And in cases like the Oculus, you actually, well, the Oculus Rift is not a good example because the Oculus Rift does have wires, but in any case, you can do with a lot fewer wires on the person themselves. So the Oculus Rift, because it used an external tracker, unlike the Oculus Quest, it needed these retroreflective markers built into the headset, and the IR sensors can find them this way. And there was this OptiTrack demo at SIGGRAPH 2019, and you could see that it can record really complicated animations pretty accurately, but as you can see, there's a lot of equipment. There are sensors everywhere, and you don't, because passive markers you usually just record the positions of the point and then fit a skeleton to them. you don't necessarily need to know exactly where the markers are prior to trying to reconstruct or track them in the game engine if it's a pre-recorded sequence. Like that only has to be done once, so I guess the same is true for active markers. A lot of it is just point fitting, so if you have enough of these surfaces, you can figure out where the skeleton is, because you would essentially grab a couple of points and try to fit a line and then place a skeleton there. That's an extreme oversimplification, but that's more or less how it works. Then we have markerless methods, which are becoming more and more important. This is done by feature tracking, and I'm not going to go into detail about how the methods work. A lot of people in this class are in the computer vision class as well, so you might have some high-level understanding of what's happening. The benefit of these methods is that you don't really need that much equipment. A lot of the times you just need a camera and some lights. And we usually use these methods for human faces because human faces are really well defined. And I have some high-level explanation of the method in a bit, but markerless tracking is used for like this kind of reconstruction or tracking where the person doesn't need a bunch of sensors around their face. You're just blasting them with lights so that they're pretty uniformly lit, and apart from that, you're just using computer vision on the camera that's recording him. And it works pretty well, but these methods are hard to understand compared to like just fitting a line to a bunch of points. In AR and VR, we use markerless tracking a lot because it works with a lot less equipment. So like I said, you only need one camera plus lighting usually. It can work with weaker devices because a lot of markerless tracking methods use machine learning, meaning that they have trained on data already, and now they just need to do the prediction, which, calculating the actual prediction based on a trained data set is relatively trivial. It's the training that's usually the hard part of machine learning. So anyway, this means that you can do the tracking with weaker devices, like the iPhone X, for example, had 3D face reconstruction. We use markerless tracking to track the environment, and we'll see some examples. So, for example, finding the correspondence between the physical and virtual environment. In VR, an example that you've seen already is that the Oculus Quest has inside-out tracking. So the Oculus Quest has a bunch of cameras on its side of it, and it can use that to track where it is in the environment. In AR, we would use this for the alignment of the virtual and physical world, which I guess we'll see on Friday. We use markerless tracking to track people. So even a lot of older devices like the PSI, which was a device for the PS2, I think, originally, which is, that's many years ago. Even the PSI could track basic bodies and skeletons. And really it just, it was a really rough estimate and it didn't track that well, but it could still do it. And the Kinect itself can track the entire body pretty accurately. We can track faces, so I just showed you the example of tracking the face with a single view camera. We saw an example before, and I'll also re-show you it in a second, of when you have cameras embedded in the VR headset that can track your face. So we saw that example of doing lip sync with these types of cameras. Then markerless tracking is used for reconstruction, which is a more recent trend, doing real-time reconstruction, and we'll cover some methods later if we have time. But for example, say that you want to recreate the person as a 3D model for the game. This is called pre-scanning. You would need reconstruction for this, and the reconstruction method needs to know where the camera is. So markerless tracking basically gives you the camera pose. You might want to reconstruct some more complex motions like blinking, or if the person is interacting with another object, you might need to do some sort of reconstruction to figure out how that interaction works. Also, say that you want the virtual environment to actually be the physical environments, just reconstructed, which is pretty common in AR because we want to know, we want to have collision meshes for the walls. So this is what you might use that for. Just to give you a very rough summary of how markerless tracking can be done, at least relative to the face. We already know the features of faces, and this is a pretty standard layout of features. I don't remember the paper that this came from, but you know, this is really, really common. You can do the feature matching of these specific features with computer vision. Those of you who are in or have taken a computer vision class will already know how this works. You essentially try to find correspondences in, well, a computer vision algorithm might generate a ton of features for this guy based on things like gradient, so a sudden change in color. Usually a sudden change of color is the main method that's used, but in any case, computer vision will by default generate a ton of features, and then you try to figure out which of those features, which of those edges essentially corresponds to the edges in the feature map. Then, as far as the 3D graphics part goes, you might use these feature locations. You might project them onto the mesh so that they can be used as control points for your animation, like a blend shape or a skeletal animation. Then as for how the features move, we have a depth problem that we'll see in a second, but generally you project it from 2D space into 3D. So for example, if you draw a box around this guy's face and then zoom in on it so that it's approximately the same size as this box, then you could sort of just project the points backwards. That might be an oversimplification. It's also not a great method, but that's something you can do, I suppose. It's a really naive way of doing it. Then movement along depth is harder because in a camera image you don't have depth, or at least in a single view camera you don't have depth, you just have X and Y of each of the pixels. But you can figure out how far each of these feature points are in terms of depth based on things like monocular cues, machine learning, so you can learn which motions would be natural. We also have depth sensors, which we'll see whenever we get to Reconstruction. Fortunately, faces are still pretty easy, even in the case of depth, because facial control points don't really change that much in depth. They tend to move along the surface of your face. So, the muscles will pull a feature point along the skull, but not into the skull. So, you can you can guesstimate where the skull is and use that to figure out, if this pixel has moved some amount of, or if this feature has moved some amount of distance over time, where would it be relative to the skull? And this is a very simplified version of the method. Just to recap on monocular depth cues, these are just depth cues that you can figure out, or this is how you can figure out depth with just using a single eye or camera. So this resource was pretty good. So you have occlusion. I think it's also called interposition, where one object is in front of the other, so you know that this object must be in front, or it must be closer to the camera. You have relative size, so if you know that in 3D space these two cylinders are the same size, but relative to the camera image this one is smaller, that means that this one must be farther. Shadows, if something has a smaller shadow on a surface relative to how big it is, you know that it's farther from that surface. There's shading. Shading is harder to describe in terms of depth. I don't think shading is used as commonly, but if you want to know where something is oriented, like the sun, for example, if you want to know where the light source is relative to this ball, in this case, the light source is above it, pointing down. In this case, it's below it somewhere, pointing forward, and it's probably also closer to the camera because it's a spherical light, it seems, and most of the sphere is visible to us. Distance to horizon, so this is related to linear perspective, so if you trace two lines that you know are parallel, in an image they will actually intersect at the horizon, and so the closer that an object is to the horizon, you can sort of estimate that it's closer or it's farther from the camera. You have to be smart about it, but anyway. Texture gradient is when objects that are closer to the camera appear more detailed. So if you're looking at dirt, for example, the dirt that's closer to the camera will have more details that are visible to you, whereas the dirt that's really far from you will just look brown. Anyway, some cool examples of reconstruction that I wanted to show you from last time. or markerless tracking as well. A lot of Reconstruction uses markerless tracking, so there are very related methods, but Reconstruction itself tends to be closer to AR, which is why I won't cover it just yet. Anyway, Kinect Fusion was a really important Reconstruction application that came out soon after the Kinect was released for the Xbox 360. And this is a method that it uses a single Kinect to reconstruct like a room or a bunch of objects. And all you have to do is sort of move the Kinect around the entire room and it will reconstruct it. So this is a cool paper, and it also changed the reconstruction industry in general, I would say, because the Kinect was such a cheap device compared to previous depth sensors. And the Kinect itself as a device doesn't have any way of tracking itself, but you can use computer vision and markerless methods to figure out where the camera is and how much it has moved between frames. So this is Kinect Fusion. It's a really old paper. I think it came out in 2011 maybe? It's not, I don't think it's 2016. Let's see. I thought it was older than this. Yeah, 2011. Anyway, this is a cool paper if you ever want to read this. But there are newer methods which are a lot stronger. So for human reconstruction, we saw this paper already, which it still uses some system that's sort of similar to Kinect Fusion. At least some of the features are similar. But they have some embedded cameras that are looking towards the mouth, and they're using that to figure out the blend weights of some blend shapes, and they're not reconstructing him because this isn't his face, but they're tracking his lips and applying it to some other avatar. And they can do that with a lot of other people. Because, I mean, generally mouths look pretty much the same, so it's not very hard to find features of a mouth. But yeah, we already saw that. There was this other cool paper called EcoCap, which is another pretty old paper, but what they did was they tracked... We saw OptiTrack, where you have a bunch of these trackers that are external. In this EcoCap paper, what they did was skeletal tracking with only egocentric cameras. So they have these fisheye cameras. Fisheye cameras are these cameras that have an extreme amount of radial distortion, but what they can do is see the peripherals better. But anyway, they were doing skeletal reconstruction with just these fisheye cameras, and they did it. They did it markerlessly, so they have some computer vision algorithm which roughly approximates the joints, and then it draws lines between them. And there are more details that you can look up yourself if you're interested, but this is a cool paper. And I think that a lot of VR and AR devices are, as they get stronger, like the Oculus Quest and the HoloLens 2 and other devices like that, this becomes more and more feasible to do real time. Right now, right now I'm pretty sure it's not real time, but I could be wrong. I think they record the sequence and then they reconstruct it afterwards offline. So the cameras just save the videos, and then the actual tracking is done at some other point. But yeah, this is a cool paper. Some work at UNC is also extending that paper. An expansion on Kinect Fusion was called Dynamic Fusion, which was Kinect Fusion except it can reconstruct dynamic objects, which Kinect Fusion could not. So Kinect Fusion could only reconstruct perfectly static things. If you tried to reconstruct something dynamic with Kinect Fusion, the tracking would break because the markerless method they were using wasn't smart enough to know when features can move, such as when somebody is talking while you're trying to reconstruct them. So Kinect Fusion would see that this lip moved, and the algorithm would be like, oh, well, that's not the same person anymore. Or, that's not the same feature. Dynamic Fusion was a little bit smarter about that. So they're still only reconstructing static people, I think. Or I think the goal is to reconstruct people statically, but I think they can still do, yeah, I mean, obviously they can still do the dynamic reconstruction, but I think the goal was to be able to do static reconstruction with things that can move. So for example, if you're trying to reconstruct somebody and they're T-posing, it's really hard to hold a T-pose for more than a couple of minutes. And so somebody might move a little bit, and so you don't want that slight movement to destroy the reconstruction as it would in Kinect Fusion. But anyway, that's what this paper is about. This is a system that's also kind of similar to Kinect Fusion, except what they were doing is they have tons of depth cameras around them, and what they're doing is dynamically reconstructing. Actually, I don't think the reconstruction is dynamic. I'm like 99% confident that this cannot be done real time in the current state of the art. But in any case, what they're doing is reconstructing really complicated dynamic scenes. Dynamic as in it's not reconstructed real time, but that the people are moving. And they did a pretty good job, but their setup was very expensive. So you could see that they're figuring out the meshes, and they're using markerless tracking to try to keep the vertices in the right place between frames. Because if you did this without a markerless method, what would happen is that the entire body would do that thing that you're seeing in the face. Like you can see that sometimes the face joints just totally change because I guess the markerless tracking just gets confused. Without any kind of markerless tracking, it would just constantly be doing that on the entire body. So anyway, you can see that they can reconstruct some really complicated scenes. And yeah, their results were really good. It's just that, yeah, this is not something that you could do with like commercial devices without a lot of effort. There's a lot of offline computation here. But even so, it's still pretty cool, and like these things are really impressive, these physics simulations. It's almost like using a geometry cache, except on real reconstructed meshes. Anyway, moving on. This paper was similar to Dynamic Fusion. In fact, I think it came out the same year. And while Dynamic Fusion, like I said, I think its goal was to... Maybe I have it reversed. I think Dynamic Fusion was trying to reconstruct the dynamic mesh, but this method was trying to reconstruct the static mesh from people that are moving dynamically. At least that looks more like what this paper is about. It's hard to tell. There are a lot of reconstruction papers. Let me move on to their results just to show you. So they messed it up at first. Well, we'll talk about this in reconstruction, but originally they had trouble aligning all of the views as the person was moving, but then they used this method that we'll see later to try to align them correctly and then remove errors. Anyway, moving on to their results. Let's see. I mean, from this video sequence where this woman's constantly moving, they can reconstruct a pretty good static mesh. The textures aren't great, but I'm guessing that that has more to do with using a low-res camera. Because this camera view is already like not that detailed. It looks like it's like 720p or maybe even worse than that. I mean, this is a pretty cool application, so let me move back. He has this jacket which is constantly moving as he's rotating it around, but you still get a pretty good reconstruction because the markerless tracking figures out the features pretty well. It doesn't have textures though, which is sad. We saw this example way earlier when we were talking about telepresence. This is called Partition, where they do the reconstruction, and then they do the reconstruction in real time, I believe, and then they send it to one of these AR devices so that the other person can see the hologram. And I think that their setup was really specific and expensive. Like you can see these cameras on these pedestals around them, and you have these pretty nice uniform lights, but they would be expensive for a commercial device. But anyway, their goal is to reconstruct people and then send them to some other device. So, like I mentioned, you know, if you want to reconstruct your own body and then send it to VR, you would need to do something like this. But anyway, this video was done in a very like advertisement-y way, and I showed this example of we try to. The goal for this paper that we did at UNC was to, let me show the outdoor scene because it looks better. The goal was to try to, so we saw EcoCap a couple of minutes ago where they were trying to reconstruct the skeleton based on egocentric cameras. The goal of this paper was to reconstruct the person or the environment and track the person and apply it to some pre-scan. Whereas that paper that we saw before, EcoCap, its only goal was to figure out the skeleton and nothing else. So we had a more complicated use case, and you know, as an initial attempt, the results weren't bad, but it's still hard to do. And we were using Raspberry Pi cameras, which are not great. Here are some examples of room reconstruction. So there was this paper that also came around the same time as Dynamic Fusion in those papers called Bundle Fusion, and their goal here is not to reconstruct people but the room itself really accurately. So they just have, we actually have one of these in the lab. It's called the structure sensor, and all you have to do is open this app and move your camera, move your iPad around, and it will figure out the room reconstruction, including the textures and stuff. And this guy's going around trying to reconstruct it really accurately. I just want to move on to the textures. You could see that, you know, they also get, actually the textures don't look as good as I thought they did. I mean, they're not bad, but actually they are pretty bad. But more recent methods, like some that were developed at UNC, can do texturing a lot better. There were some 2019 papers from NVIDIA and from UNC that do this better. Bundle Fusion, I think, is an older paper. I think it came out 2015. But even so, the method is cool. And they use the markerless tracking methods to, you know, they use it to figure out where the camera has moved. And when it does the reconstruction of like one perspective, they have to do some tracking to figure out where is that perspective relative to the entire room. There was this cool AR application called Room Alive where what they did was they tried to reconstruct the person's room, like the room of the person who's playing the game, and then they used the surfaces of the room to essentially have these AR games. So they figure out where the walls are, where the floors are. They dynamically figure out spawn points, things like that. As you can see, they had a really complicated setup. Well, what they did was the reconstruction was done with the Kinects, and the projectors, essentially they compute the image that the projector needs to show for the image to look like it's projected correctly on a 3D object. So let me move on. So for example, how do they make this guy look like he's walking on the floor? How do they make this one look like he's walking on that bench? And things like that. And this was an old paper, but it was an interesting proof of concept. This is an example of a paper where it's a little bit too heavy on the hardware setup. Obviously this wouldn't be, you know, this wouldn't be ideal for a commercial setup. But even so, interesting idea. They have a couple of these games, and you can control this guy who walks around your room. Here is a more commercially practical application, and this came out in 2014, but when the iPhone 10 came out and it had a depth sensor in its front-facing camera, people were a lot more interested in this kind of technology, essentially doing reconstruction for augmented reality with just a phone camera. And they used almost entirely monocular cues for this. And I think they used some features of the phone hardware, like the accelerometer, to make corrections. But yeah, what they do is they try to reconstruct the room with just the phone camera, and then you can place objects on like your table, and you can ride your car up this piece of paper. And you know, for 2014 smartphones that had single cameras that weren't particularly good, their results were actually pretty nice. And the important part is that it works with commercial devices like smartphones, whereas a lot of these other reconstruction methods don't. So anyway, those are some interesting use cases of reconstruction, and now we can talk about kinematics, which I've teased for a while. And kinematics as a field it's essentially, this is kind of where robotics and graphics as fields intersect with each other. A lot of the concepts that we use came from robotics, and they were perfected in graphics, or at least they had different goals in graphics. You're essentially trying to figure out where the transform of different parts of the body, for example, are relative to the parents. Because remember that when we have skeletal animation or some setup like that, we are restricted by this tree structure, and so we need to know local transforms. So kinematics tries to solve these types of problems. And in a robotics context, what you would have is an arm like this with a little, a hand like this that's trying to grab things, and you want the hand to go grab something and then figure out where the joints need to move, or how they need to rotate to get the arm to that place. But anyway, that's way too simple. I'll go over some terminology. So a rigid body, most of you have had experience with rigid bodies at this point because they exist in Unity, and they exist in Unreal as well, but they're not called that. But a rigid body is just some non-deformable object which is constrained by physics. So it might have gravity limitations, it might have, it might be restricted by the physics of some other game object. The important part is that it's non-deformable. So if you have like a cube that has gravity, that is a rigid body. If you have a piece of cloth that can change shape dynamically, and it has physics like gravity or so on, that's not a rigid body, that's a soft body. And soft bodies are not very common in game engines because they're computationally really expensive, so we won't talk too much about soft bodies. A manipulator is any device that's capable of manipulating things in the environment. So, for example, on this robot, the manipulator would be... the definition seems to vary a little bit, but some people would consider the entire arm the manipulator, some people would consider only the hand the manipulator. But usually we think of manipulators as a kinematic chain of components, which in robotics and graphics will usually be rigid bodies, and they're linked by joints. So in this robot you have a chain of joints, so you have... Actually, let me go through the rest of my definitions. Well, okay, the joint is, like right here, the joint is joining these two rigid bodies, this big piece of machinery here and this other smaller one. For a human skeleton, you have, biomechanically, I think it's pretty obvious what joints are. And I talked about them in skeletal animation, but you have joints for your neck, your hips, or spine, or however it's done. You have joints for like each thing that can rotate or translate independently, so like shoulders, elbows, and so on. Joints that you can actually control are called actuators. So I mean, you're free to look at your hand and try to figure out what this means, but your knuckle is an actuator because you can actually, can you? It's hard to think about biomechanically what you can or can't control, but I'll have to think about it. But you can control some parts of your body. Like you can, like you can tell, I don't know, it's, God, this is hard. It's psychology. You can essentially tell your body to move your shoulder a certain amount, and your goal is to move your hand or your elbow a certain amount, but you can't control directly certain parts of your limbs. Like you can control your wrist, for example, but you can't control like the middle and proximal bones, which are like the two bones that are between, or the two joints that are between the tip of your finger and your knuckle. You can't control those, but what you can control is the tip of your finger and your wrist and maybe your knuckle. I don't know. I'm thinking to myself, if I can think to this is going to sound really dumb, but I'm trying to think if I can tell my brain to move my knuckle, and it's too difficult. I'm breaking my brain trying to think about that. Anyway, somebody who knows more about physiology can answer that. Anyway, that's what an actuator is. It's just a joint that you can actually control yourself. Robot arms, human arms, and so on, structures that are called limbs, or structures that represent limbs, are usually seen as the manipulator itself. So, like I said, there are two, like I said, it's vague, but, or I mean, it varies a little bit, but I think the more generally accepted definition of manipulator is it's the entire limb. The end effector is the final device in, I don't know why I wrote change. This should be chain. The end effector is the final joint in the chain of the manipulator. So for this robot, this little grasper thing is the end effector, because this is the thing that you're actually trying to cause to reach some point. For a human, you would generally consider the hands or any of the leaf bones essentially to be the end effectors. So if I want to move my foot to a position, I need to rotate my knee and my hip, but those are not the things that I'm trying to move to a position, but I do need to rotate them to get the end effector to a certain point, if that makes sense. The same is true for like your arms. If I want to move my hand somewhere, or if I want to move my finger somewhere specifically, let's say I want to move my index finger to my desk in front of me, I need to move all of the parent limb, or all the parent joints, to get the finger to that position, because the finger is the end effector. And technically it doesn't matter where the other joints are as long as I get my finger to that position. So the finger in that case is the end effector. If you make a fist instead and you don't really care about the fingers, then maybe you would consider the fist itself to be the end effector. It just depends on what you're trying to do, but hopefully that makes sense. So forward kinematics, this is the simpler of the kinematics methods. If you already know the transforms of all the parent joints, where is the end effector? And here's just one of the super robotics-y figures that shows us. I don't think the robotics figures are the easiest to understand for us game developers or VR developers, but you can think of it as this is very similar to the method that we use to get the world transform of some game object from a bunch of local transforms. So you might recall this old slide where we were converting from local to global space, and what you would basically do is, if you think of this parenting structure as like a tree, in this case the red cylinder would be the leaf and the test scene would be the root. If you traverse upwards and you have the relative transforms of all of these things, what you would do is you would traverse upwards, you would add the locations and rotations, and you would multiply the scales all the way till you reach the root, and after that you don't have to do anything else. The root is, I mean, it's the root. And sure, you could keep doing it, but the transform of a root relative to itself is just essentially the identity transform matrix. The position 0, 0, 0, rotation 0, 0, 0, scales 1, 1, 1. So if you keep going through this process over and over again at the root, the result won't change. But in any case, in Unity, and I think this makes more sense now that you've done a bunch of assignments, but in Unity and Unreal, the name of the level is considered the world origin. So where is 0, 0, 0 considered in 3D space? And if we saw this example in the very beginning of the class where the test scene is the root. The blue plane is the immediate descendant of the root, and I defined it as 0.1 meters high globally and locally. The reason that both global and local transforms are the same is because it's attached to the root, which is, that's as far up as we can get. The white plane, which is a child of the blue plane, was 4 meters higher than the blue plane, which means that it's 4.1 meters high in terms of global space. Because remember, we just add the locations. In this case, we're only worried about height. And then the red cylinder is 1 meter higher than the plane, which means that it's 5.1 meters high globally. So hopefully that makes sense, especially now that you've done the assignments. But we have some issues. Forward kinematics it's pretty simple. I mean, I think that this is relatively intuitive, this example, and just what we're trying to do in general. But the problem here is that we need to know all the parent joint transforms. So if you think about each of these things in the system as a joint, we already know where they are relative to each other. So for example, if I just want to find something that is attached to the red cylinder that is zeroed out, I can already easily figure that out because I know where all these parents are. The problem is that we don't always know that. So we're pretty close to the end of the class, so I won't, no need to answer a question, but can we animate a VR character with only forward kinematics? The answer is not really, because commercial devices, and I mean, you've used the Oculus Quest, so you have a good sense of this. Commercial devices really only track the head-mounted display itself, so they track where your head is and they track where the controllers are. They don't really bother to track anything else. Especially nowadays that we have inside-out tracking devices like the Oculus Quest, these devices have cameras which are pretty much only in the front, and so they can only really see in front of you and maybe some of your peripheral. And you have some examples like the Oculus Rift S, which has a downwards or an upwards facing camera, but even so, it's the amount of your body that it can actually see is really limited. So all of you have gone through the Guardian setup process, you know more or less what the range of this camera is. It's really not that much, it's actually more restrictive than your real life peripheral view. And if you think about it, like if you're looking directly forward and your arms are like on your armrest of your chair, can you see your elbows? Not really. And so we have the same limitation with these VR cameras that are common nowadays. I should use my pointer more. So technically, if you wanted to, you could use some external tracker or extra cameras around the headset to track more joint positions. But the problem is that tracking tech isn't quite there. And another thing is that the extra cameras have other limitations. Adding more cameras to a consumer device is pretty expensive. You can also ruin the ergonomics because you need to change the headset to be, you have to deal with the weight distribution of the headset. You need to push wires through things, like say that you wanted some camera on the side of this headset. You need to somehow get the wire through the top here, and that would in turn make the headband here less flexible. And there are all kinds of ergonomic considerations. You would need to place them pretty specifically. And the problem with cameras, those of you who are in the computer vision class will know this, but the problem with cameras is that if you want them to track accurately, you need to do extrinsic calibration, which means that you need to know where the cameras are relative to each other pretty much all the time if you want them to all track the same object. And that's hard when, if you were to attach the camera to anything but the rigid front part of the headset. You know, if you wanted to put the camera on the side here where the face mask itself can push the camera in and out, if you want to put a camera at the headband, where like the entire headband can rotate up and down, all these things make extrinsic calibration harder. And so you need to place them really specifically, and in a lot of cases you just can't place them in a certain place at all. Like, you know, the headband, putting a bunch of cameras in the headband might sound like a good idea in theory, but you can't really do it because it's so flexible, and so there's so many degrees of freedom. Cameras use a lot of hardware resources. A lot of cameras by default, I think, use a lot of CPU resources, and CPUs on mobile devices are really weak, generally. I mean, they are getting better, but they're certainly not i9s. Also, even if you add a ton of cameras to the headset, like let's say that you had let's say that you have a perfectly rigid headset, and you add hundreds of cameras to various parts of the headset, you would still have occlusion problems, because no matter how many cameras you add, it's still possible for you to orient your arm in such a way that you can't see the elbow, for example. Like if you, I mean, we're not in a physical location, so you can't see me. If you just you can pose your body such that you can't see the elbow from any angle without moving your head. Or, I mean, what else can you do? I mean, imagine moving your elbow under a desk or something like that. There are a lot of things that can cause certain parts of your body to be occluded. Something that we at UNC, with our egocentric work, struggle with is legs in particular, because when you're standing up, your legs are pretty much always occluded to cameras that are on the headset. So, you know, it's a challenge to design a headset that has cameras that can see your legs that don't cause the headset itself to be gigantic. So, you know, it's tempting to make antennas like EgoCap did. They have these antenna-like things that they added to the headset. It's tempting to do that for research, but obviously this isn't ergonomically feasible. Oh god. Yeah, you can't really use external cameras in general anymore, because we're moving away from external trackers. We want to minimize hardware setup. A common complaint in VR in the initial days of the Vive and the Oculus Rift was that there were too many wires and too many things to set up. The Oculus Quest is convenient. It doesn't really have anything that needs setting up. So, you know, we're trying to make more Oculus Quest-like devices, which means that we need to stick to any kind of egocentric camera. So we need smarter methods of predicting the transforms of things that we don't immediately know from the tracking system, which is where inverse kinematics comes in. So if we think, let's say that we only know the end effector and its constraints on the parents. So for example, let's say that we have pretty much the same structure as before, except in this case we only know where the cylinder is, and we know the constraints on the parents. So in this case, which one is the end effector? It is the cylinder itself, because that's the leaf of this tree structure. And in the inverse kinematics case, we want to know, we're trying to figure out the transform of the parents themselves. So here I have constraints. I say red is 5.1 meters high globally, and I tell you how far the white plane can be from the cylinder, and I tell you how far the blue plane can be from the white plane. And from there, you essentially propagate backwards and figure out the transforms of the parents. And which of these things we want, like do we want global or local transform? Do we want the local transform of the end effector? Like do we want to know where it is relative to white? This all depends on your use case and the game engine's API. And, you know, are you doing animation or not animation? Are you doing robotics? It really does depend on what you're trying to do. We're at 450, so I can't really move any further, but Next time we'll see the more complicated rotation example, which hopefully will prime you for the actual IK material. So yeah, you're free to leave. Bye.